In this video, we solve problem 14.5.008 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the area of a surface given by f of xy that lies above the region R. And in this case, f of xy is y squared and R is a square with these vertices in the xy plane. The first thing I always like to do with any of these problems is to sketch the surface so that we can have a better sense of what's going on. So we're sketching in three-dimensional space, and we have z, that's f of xy, is equal to y squared. So that's telling us that z is equal to y squared back in the yz plane. Remember that yz plane is back here. So when y is 0, z is 0. When y is plus or minus 1, z is plus or minus 1 squared, which is 1. When y is plus or minus 2, z is plus or minus 2, quantity squared, which is 4. So really, we just have a parabola in the yz plane. And that's what it would look like if we were just graphing in 2D, but we're graphing in 3D. Remember what that means. If this equation only involves two variables, and it does, then the third variable, the missing variable x, is free to be anything. So what we have is a cylinder, z equals y squared. It's a parabolic cylinder. And we say that the rulings are parallel to the x-axis. Or in other words, we're looking at all of the lines that are parallel to the x-axis that pass through this parabola in the yz plane. Basically, you're going to see exactly the same parabola for all values of x. And we're going to go up to x equals 5. This is not to scale. But when x equals 5, we're going to see the same parabola over here. I'm just going to do the best I can. I'm going to wing it. That's not a very good parabola. That's okay. So roughly like that. Does that make sense? So you've got this, it's like a sheet. Yeah, I've sort of drawn it a little weird on that side. But basically, we've got a parabola that looks like this. If the z-axis is pointing straight up and the y-axis is going this way and the x-axis is coming out of the page, that's what that surface looks like. Okay, now we're not actually interested in the surface area of the whole thing, because that would be infinite, of course. We're just interested in the surface area above this rectangle. So we want, it's a rectangle or a square, excuse me, with a vertex at x equals 0, y equals 0, at x equals 5, y equals 0, at x equals 0, y equals 5, so that's that right there. And I'm just going to use this as a straight edge now and try to draw something parallel to that y-axis. Not doing a very good job for some reason today. It's okay. We just do the best we can. And then I want to draw something parallel to the z-axis. This is when I always feel like Bob Ross. There we go. Okay. So we have 0, 0, x equals 5, y equals 0. And of course, z equals 0 there. Y equals 5, x equals 0 is right there. And x and y both equal to 5. That's right there if we're in the xy plane. I really hate even writing that ordered pair. This should really be 5, 0, 0, 5, 5, 0, 5, 0, 0, and 0, 0, 0. But this is the region that we're integrating over. This is the region R. So basically, we want the surface area of this surface that part of that surface that lies above the region R. Obviously, I haven't drawn it far enough. When y equals 5, z is going to equal 25. So it's going to be way up here, and you're going to have this parabolic surface. And we're actually not going to calculate that surface area at all. We're just going to calculate the surface area of that part. So you've got something that looks like this. And basically we want that surface area from y equals 0 to y equals 5. Okay, so that's helping us visualize what's going on. Now to calculate surface area, we're just going to use this formula. We derived it in another video. It's a double integral over r of the partial of 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared. And then we take that expression and we take the square root and then we integrate over r. Now r is really simple. Clearly x goes from 0 to 5 and y goes from 0 to 5. So that's pretty easy. So it really doesn't matter if we integrate with respect to y or x first. I will integrate with respect to y first, and I'll give you a reason for that in just a moment. Now I just need these two partial derivatives. You could call this the partial of z with respect to x if you wanted to, and you could do the same thing over here. Call that the partial of z with respect to y. It's the same thing because z and f are the same thing. And the partial of z with respect to x is 0 because there are no x's in that. The partial of z with respect to y is, of course, 2y by the power rule from Calculus 1. So you've got that right there. Now, typically I would square the 2 and square the y and simplify, but it's actually helpful to have it in this form. If u equals 2y, this is 1 plus u squared, and it's under a radical, and we're going to have a constant to compensate for that 2. This is not an integral that we know. It's not one of our basic rules. We always ask ourselves, do I have a rule for that? And we don't have a basic rule for this. And then if we don't have a basic rule, we say, can we use u sub? It turns out we can use u sub, but that's just going to get us to the point 1/2 of the square root of 1 plus u squared here. Now that 1/2 of the square root of 1 plus u squared, if that were our integrand, we can evaluate that with a trigonometric substitution. So that's what we're going to do. I am going to choose not to do the definite integral here. I'm going to focus on doing an indefinite integral, and then we will use the antiderivative that we calculate to come back and solve this problem. Okay. We can't get away from trig sub, unfortunately, on this problem. So let's just do this indefinite integral and let u equal 2y. Then du equals 2 times dy. And if I want to get dy by itself, I have to divide both sides by that too. So this becomes the integral of the square root of 1 plus, that's my u squared, and dy is 1/2 of du. Remember, when you're doing a u sub, you're basically replacing everything with something else in terms of the new function u. It's a literal replacement. Instead of writing what dy, we're going to write a 1/2 times a du. Okay, and again, we don't have a basic rule for this, but that's a u squared plus 1 squared. So we can use a trig substitution with u equals a, which is 1 times tangent of theta. So let's write that down. We'll say since the integrand involves u squared plus a squared, we let u equal a tangent of theta to evaluate this antiderivative. In order to do that, we need to identify a, A squared is 1, so of course A equals the square root of 1, which is 1. And because of this u squared plus a squared, or 1 plus u squared, we're going to let u equal 1 times tangent of theta. Then we compute du in terms of theta. The derivative of tangent of theta is secant squared of theta. So du is that derivative times d theta. Don't forget your d theta. And then this square root is something we also want to simplify. The square root simplifies nicely when you make this trig substitution. That's why we use trig substitution. If u is tan theta, this is 1 plus tangent of theta, squared. And 1 plus tangent squared theta is secant squared theta. And the square root of secant squared is secant. So we choose the appropriate u, we compute du, and then we simplify that square root. In general, you can just simplify the a squared plus u squared. If you happen to have a radical, it's helpful to simplify that as well. Okay, so we see that we need a trig sub, then we do this. All of this was preparing to substitute. If I think about trig substitution, I think of it as comprised of 4 major steps. And here's the big step: prepare to substitute. We did it. And now you're going to substitute. Write everything up here entirely in terms of u, or entirely in terms of theta. So we've got 1/2 of the integral, and the square root of 1 plus u squared can be replaced by secant of theta. And here's where a lot of students make a mistake. Don't forget to substitute the du. Du is secant squared theta d theta. And we can simplify that. We have the integral of secant cubed, or the antiderivative of secant cubed. But if you go back to your trigonometric integrals guidelines, you'll see that if you have the integral of secant to an odd power where there are no tangents, what they recommend is, factoring that secant to an odd power, writing it as a secant times a secant squared, like we have here, and then using integration by parts. So I'm not going to simplify it because I knew that the integration by parts is coming. And if you're saying to yourself, how did you know that? You might want to review the Trigonometric Integrals guidelines. Trig Integrals guidelines. They tell you if the power of secant is odd and there are no tangents, do this. And that's what I'm remembering and then applying here. So we prepare to substitute. The next thing we did was we substitute and then we simplify. And compute the antiderivative. After all, that's the reason why we did the trigonometric substitution, was because we thought that if we were to do that, this would simplify to something that we could compute the antiderivative of because we're familiar with trig integrals. So we look at the guidelines for trig integrals and they say, let's use integration by parts where u is equal to that odd power of secant that's left, and dv is secant squared theta d theta. Or we can include that in our u as well. So we've got u equals 1/2 of secant of theta, and we need to compute du. dv is secant squared theta d theta. We want to differentiate to find du and anti-differentiate to find v. The derivative of secant of theta is secant of theta times tangent of theta d theta. or du is the derivative times d theta, and dv is the antiderivative of secant squared, which is tangent. And then whenever you're using integration by parts, remember, if you set up this 2 by 2 table like this, it works this way. You want to multiply across that diagonal and multiply across that diagonal and subtract. It's uv minus the integral of v times du. Don't forget to actually anti-differentiate this. The integral part is really important. Okay, so we had 1/2 of the integral of secant cubed theta d theta is u times v. So that was 1/2 secant of theta, that was our u, times v, which turned out to be tangent of theta. If you're saying to yourself, how did you get that again? I'm just remembering what we had down here, u times v, minus the integral of v times du. Notice with v times du, I have a 1/2, a secant of theta, and a tangent times a tangent is a tangent squared, and don't forget your d theta. So according to integration by parts, we get uv minus the integral of v times du. Now, a lot of students make the mistake of trying to anti-differentiate this and anti-differentiate that and multiply. It doesn't work that way. You have to simplify this first. And if you look at your Trig Integrals guidelines, they will remind you that over here, when you've got this secant of theta times tangent squared theta d theta, one way that we can evaluate this is we can replace tangent with, or tangent squared, excuse me, with secant squared minus 1. That's because of one of our Pythagorean identities, 1 plus tangent squared equals secant squared, so tangent squared is secant squared minus 1. And that whole quantity is multiplying that secant of theta and that negative 1/2. If you distribute that negative 1/2 secant of theta to this binomial expression, you're going to get negative 1/2 secant times secant squared is secant cubed. And then a negative 1/2 times secant times negative 1 is going to be positive 1/2 secant of theta d theta. And we have a rule for this. Now, if you're saying to yourself, uh-oh, isn't that the integral that we started with? You're absolutely right. The integral that we started with actually appears on both sides. Now, if it was identical, if it wasn't a minus 1/2 but a plus, I'd be worried because then probably this would cancel with this and I just have an identity saying this equals itself. Of course it does. But that's not what we have here. This sign is the opposite sign from that one. So I can treat this like an algebraic equation. I can treat this like this problem. Let's say you're in algebra class and you've got 1/2 x equals 3 minus 1/2 x plus 5. It's kind of what we have here. I've got 1/2 of what I'm looking for equals something minus 1/2 of what I'm looking for plus something else. And we're trying to get x by itself, right? If I was solving this, all I would do is add this guy to both sides. And when I do that, all of my x's are on the left. And of course, I could simplify that on the right and I'd get x equals 8. That's pretty much what we're going to do here. I know it looks much worse because it's calculus, but it's the same principle. I've got this guy here and this guy here, and I'm thinking of that as my x. That's my unknown. So I'm going to add this to both sides of my equation. I know most Calculus 2 students don't need me to add vertically like this, but just to show my work, I'm going to. I have 1/2 of those plus another half. That's going to give me the integral of secant cubed theta. And that equals 1/2 secant of theta times tangent of theta plus 1/2 times the integral of secant of theta, which is natural log of the absolute value of secant of theta plus tangent of theta plus c. And that's that. We've computed the antiderivative. Now let's look at the original problem. We had this, and we were actually saying that this was equal to the 1/2 of the integral of secant cubed. So that means that 1/2 of the integral of 1 plus u squared is 1/2 of the integral of secant cubed theta d theta once we do our trig substitution, and 1/2 of this is 1/2 of this expression. 1/2 times that 1/2 is going to give me a 1/4. And this 1/2 times that 1/2, remember it's got two terms, so you have to distribute that 1/2 to both of them. It's going to give me a 1/4 natural log of the absolute value of secant plus tangent. And that half of that c is just going to be a different c. I'll call it c1. If you want, you could keep it as c, but it's technically a different c. Okay, now remember we used trigonometric substitution to evaluate this integral, and eventually we want to get back to an expression involving u. This theta is just something that we made up so that we could evaluate this. So we have to use the fact that u equals tangent of theta to write all of this entirely in terms of u now. So usually when we're doing a trig sub, we've got this answer and we're writing it in terms of u. In order to write this in terms of u, we're going to draw a triangle. We're going to label the sides of the triangle in terms of u. Just using right triangle trig. Tangent of theta is u over 1, and we remember from SOHCAHTOA back in trigonometry class or pre-calculus in high school, tangent is opposite over adjacent. So if I draw my triangle like this and I put my angle theta down here like this, the side opposite theta is u, and the side adjacent to theta is 1. And then by the Pythagorean theorem, this squared plus this squared equals that squared. So this is the square root of 1 plus u squared. You don't have to remember that every time. You could just look at the triangle associated with the tangent substitution on your trigonometric integrals or your trigonometric substitution reference sheet. That would be fine. Or you can just do this. So we've used this initial substitution to label two sides of the triangle, use the Pythagorean theorem to get that third side, and then you look over here at your answer, and basically what you want is you want every trig function in your answer to be written entirely in terms of u. Now we already know that u is equal to tangent of theta. So every time I see a tangent, I'm just going to replace it with a u. Now I just need to find secant of theta. Well, if this is our triangle, secant of theta, remember that's 1 over cosine, or the hypotenuse over the adjacent side. It's going to be 1 plus u squared. That's the hypotenuse over the adjacent side that's next to theta, but not the hypotenuse, it's the other one. That's 1. So secant turns out to be the square root of 1 plus u squared in terms of u. Okay, and that triangle served its purpose now. Once you've drawn your triangle and labeled the sides, you write your answer entirely in terms of the original variable. Okay, so we've got 1/2 of the integral of the square root of 1 plus u squared is 1/4 of secant times tangent, which ends up being u times the square root of 1 plus u squared, plus 1/4 natural log of the absolute value of secant plus tangent plus c. Now remember, even u was something that we made up in order to evaluate this integral, or to evaluate an earlier integral. So we actually have to back substitute again. If you're wondering, what does this have to do with surface area? Remember, we're trying to evaluate this guy eventually. So this was, actually came from here. So we did get an answer in terms of u, but we don't really want an answer in terms of u. We want an answer in terms of y, and y is equal to 2u. So we'll back substitute again. Basically replacing all of your u's with 2y and simplifying. Of course, 1/2 or 1/4 times 2 is 1/2. And whenever you've got a product and you're squaring it, you square both factors separately. Okay, so we found our antiderivative of this guy in terms of y. And now we want to go back up here to our surface area integral finally. So we're going to substitute again. Surface area is the integral, the double integral from 0 to 5 of the it's the integral from 0 to 5 of the integral from 0 to 5 of 1 plus 4y squared dy dx. The antiderivative of this function is right here, but we don't need the plus c. You want to evaluate all of this from y equals 0 to y equals 5. Plug in 5, plug in 0, and subtract by the fundamental theorem. And then whatever the answer that is, you anti-differentiate with respect to x, and then plug in 0 and 5 to finish the problem. Okay. So if I replace y with 5, I get 5 over 2 times the square root of 1 plus 4 times 5 squared. 5 squared is 25. 4 times 25, that's 4/4, it's 100. So we end up with 101. Okay, I guess I didn't need that radical to be so large. And then I've got 1/4 of the natural log of the absolute value of this. But if y is 5, all of this is positive. So we don't really need the absolute value. The absolute value of a positive number is that number. So this will still be 101 under a radical. And 2 times 5 is 10. And then if you replace y with 0 here, you're going to get 0 for this term. 0 times something is 0. And then if you replace y with 0 here, you get a 0 here and a 0 plus 1 here. So you end up with the natural log of the square root of 1. Square root of 1 is 1. Natural log of 1 is 0. So it turns out that when you plug in y equals 0, this is 0 and this is 0. So we're just subtracting 0 from this, which is the same as not doing anything to it. That's a number. We're anti-differentiating with respect to x. So we just get that number. times x, evaluated from x equals 0 to x equals 5. When x equals 5, we get this times 5. When x equals 0, we get that times 0, which is nothing. So we'll end up with this expression times 5. And if you prefer, you don't have to. Actually, you may have to. We'll see if WebAssign likes it the other way. To simplify, we'd probably distribute the 5 to everything. 5 times that 5 over 2 is going to give us 25 over 2. And 5 times that 1/4 is 5/4. And that's it, that's the answer. And if you're wondering what does that mean, that's a number, it's a positive number. What does that number represent? It's the surface area of this guy. It's the area of z equals y squared above this rectangle in the xy plane.